Yeah, so I'm really enjoying the workshop and getting to know many of you and your thinking, and so I appreciate the opportunity. Look, there are three general questions about bioenergy on a scale sufficient to contribute to climate change mitigation that we might ask. One of them is it possible? The second one is it desirable? And the third one is, how do we do it? There's a lot I could say about the first two questions, and I may comment on questions 1 and 2 near the end, but I've been encouraged to focus on question 3 first, and I will do that. And I'm going to focus on liquid fuels from cellulosic biomass. Bioenergy is a broader topic than that, but I think I can use your time best by doing that. And again, I'm happy to address other things in this discussion. So I was given the title Past, Present, and Future. A few comments, I'll focus mostly on the future, but a few comments on the past. There has been a general tendency to not take the long view when it comes to cellulosic biofuels. The field has been behaving for 30 years as if it's 2 years away from milk and honey, and has actually very much delayed its fruition because of that in a continuing pattern of self-delusion. We are and probably should entertain really large infrastructural changes to accommodate hydrogen and electricity powered vehicles. I am not speaking against that at all, but I observe that there are far smaller changes required to accommodate various liquid biofuels, but the word is has to be drop-in infrastructure compatible. Now, I think there's some reasons for that, but it's another sign of this very near-term perspective when it comes to biofuels, and not being willing also to do the needed long-term innovation targeted research. We've been stuck in the same processing paradigm for 35 years. Point number 2 about the past. Reducing carbon emissions has not been a major driver of biofuel policies in most places in the world for most of the time. There are some exceptions, but by and large, rural economic development has been a larger, and essentially providing a new market for things farmers know how to grow has been, in Europe and the US over the years, the dominant driver. Not the only one, but the dominant one. The third thing about the past is that the last decade has seen a gigantic pendulum swing between tremendous investment and optimism in the roughly 2007 timeframe to today virtually no investment and much less optimism. Dan referred to that. It's not as good as people were saying then, and it's not as bad as it is now, as people are saying it is now. Okay, as to the present, in brief, there are a half a dozen cellulosic ethanol plants that have come online in the last few years. You could either call them large demonstration plants. They are not pilot plants. They are either large demonstration or small commercial. I could go into this in great detail, but basically they are too expensive to replicate, and the people that built them will say, even publicly, that a step change in the technology is needed beyond learning by doing in order to make these plants cost competitive. And my own view, and I'll try to distinguish between my views and when I'm representing what I think is more or less consensus view that can be challenging to find in this field, I think that statement I just made is even true at $100 a barrel oil. In other words, the current technology needs step changing more than learning by doing improvements in order to be competitive with $100 a barrel oil, let alone $30 to $50 a barrel oil. Now, the good news, so looking towards the technology with an eye towards the future and what could be done. Okay, the good news is that cellulosic biomass at the representative price of $80 a ton, and there's a lot of biomass available for a lot less than that, but if we're talking about really large scale, it would rise up the supply curve, is equivalent on a purchase cost per gigajoule basis, and there are other ways you can value resources, to oil at $29 a barrel. And so fundamentally, we can make that economic equation work. And if you contrast that to algae, for example, the cost of a gigajoule of algal biomass, regardless of its composition, is an order of magnitude larger than the price of the price of fuel per gigajoule. And so what that means about algae is it may be a good idea, but it's inconceivable that fuel would be the dominant economic return from algae production. It's got to be protein or animal feed or clean wastewater with fuel as a byproduct, much as the case with soybeans, for example. The bad news, so the good news is the feedstock is cost competitive. The bad news is that today's conversion technology is much too expensive. Why is that? Well, at a very strategic level, it has to do with evolution. Photosynthesis first appeared on the Earth, as near as we can tell, about 1.8 billion years ago. Microorganisms and various physical factors that might disrupt photosynthesis and the scaffolds that hold up those solar collectors, namely the stems and whatnot. Microorganisms were well established before that. So basically, for about half of the history of life on Earth, photosynthetic microorganisms have been becoming more and more resistant to attack. And if you look out the window, they're actually doing pretty well. All right? So fundamentally, it's that nature has evolved cellulosic biomass to be difficult to take apart. By contrast, if you look at a grain, at corn, for example, a corn kernel is designed to be easy for this fledgling new seedling to take apart and get energy from. So dramatically different biological function. So in strictly biological terms, that is the thing that we're trying to overcome. People refer to the recalcitrance of cellulosic biomass. What that means is basically the difficulty of making something reactive out, which usually means either a gas or something in the liquid phase, something reactive, whether it's synthesis, gas, sugars, or what have you, whatever that intermediate is, whether you're talking about biological processing or abiological thermochemical processing, it is still the cost of that upfront thing. The conversion to sugar or the solubilization of the biomass in the case of biological processing, the conversion to synthesis gas or pyrolysis oil, it's the upfront piece. Typically, once you've got a reactive intermediate, at least without a lot of contaminants, we know how to make that into something, okay? So it's the upfront piece that's the problem. So I'm going to talk in the remainder of this time, like Marty and like Yet Ming, both of whom didn't offer a comprehensive catalog of everything you could do, but said, here's something I'm excited about that I think can work. If you'd invited someone else, they might have told you something different they were excited about, and they might be right. So my point is not that this is the only good idea, but it's the only one I have time to tell you about. I'm keeping track of time. And how about it? Yeah, I'm 7 minutes in. Okay. So the approach I'm going to tell you about is a biological approach. It has only come into focus in the last 18 months. It has arisen within the context of the department. I'm critical of research funding, but I've also got to acknowledge that it's in the context of government research funding that this arose. So the DOE-funded Bioenergy Science Center, also called BESC, and it's only starting to appear in the literature, and most people are not yet aware of it, and so that is what it is. So for the last 35 years, literally, since actually my advisor Hans Gresslein invented the modern biomass pretreatment field a long time ago in 1979, so for the last 35 years, the cellulosic biofuels field, the derived cellulosic biofuels field, has functioned within what I call, and I'm sorry for all the syllables, the thermochemical pretreatment / fungal cellulase paradigm. Let me stop and explain that. It's not so hard. Thermochemical pretreatment is the idea that in order to make nature's biomass that's evolved to be recalcitrant, in order to make this stuff accessible, we need to somehow beat it up. And so the idea is thermochemical. You beat it up with a combination of heat and chemistry. You may add dilute acid, you may add ammonia, you may do steam explosion, what have you, okay? That's what pretreatment is. Fungal cellulase, there's an interesting story. It begins with canvas degrading in the Army after the Second World War when we were active in the South Pacific. Tents didn't last very long. The US Army started to do research on cellulases, and for various reasons, they picked aerobic fungal cellulases as the bugs that they started working on. Every single commercial plant today uses the thermochemical pretreatment fungal cellulase paradigm. Okay, so hopefully I got a good laugh at that, and I'm not sure it was with me or at me, but in any case, hopefully that term we can get by that. Now, it is precisely the high cost of thermochemical pretreatment and fungal cellulase that makes current plants have only their capital cost higher than the selling price of the product, when in fact you want these economics for a commodity process to be dominated by the raw material. They're not today. They're dominated by capital. Okay. So point number one is that, well, it's been known for a long time that anaerobic thermophilic bacteria. I realize I'm not talking to that many biologists here, but these occur naturally in things like hot springs and compost heaps. So anaerobic thermophilic bacteria have been known for a long time to be able to ferment cellulosic biomass without added enzymes. So, that might be one way to get rid of these two problems, that I've got to add enzymes and that I've got to beat the stuff up with heat and chemistry. 3 recent discoveries have been made. Number one, that those same thermophiles are decisively, many-fold better than the fungal cellulase that we based an industry on. So basically, we have not been working with nature's best catalyst. By the way, although there's an intellectually very rich discipline of trying to do protein engineering to improve what nature gives us, it's been almost a complete dry well in 20 years and millions of years invested. And in a way, that's not surprising because the microorganisms have been charged with this task for a long, long time. The idea that we can figure out how to solubilize cellulose better than they can might not surprisingly, has not worked out very well. So it really makes sense to start with nature's best. And we found out that those are different from what we thought. Number two, we found that these thermophiles can actively ferment cellulosic biomass in the presence of aggressive mechanical milling. They don't care. They're very, very mechanically tough. That's actually different from yeast. We did control experiments. Yeast, which is the conventional microorganism, it doesn't work at all. They're just killed by the milling. And number three, we showed that this combination of nature's best cellulolytic microorganisms and milling without added enzymes and without thermochemical pretreatment can get you 90+%, very, very high fractions of the carbohydrate soluble and therefore fermentable. Those are the 3 discoveries. So it's also true that until now, milling has been known as a way to make cellulose accessible to biological systems, but it's been rejected because the energy requirements are too high. However, that's milling material that biology has not first had a crack at. Once biology starts fermenting cellulosic biomass, the factors that determine milling energy, the viscosity and the strength of the particles, declines by orders of magnitude. So conventionally, you want to pre-treat first and then biologically process. We're talking about doing them the other way around. And at the risk of using yet more of my time, I want to impress upon you that this problem actually has already been solved. We just had to look in the right place. Okay. So my son's a dairy farmer. Oh, come on. My son's a dairy farmer. I took this picture at this video at his farm. What is that cow doing? It's chewing its cud. So basically what nature does to solve this problem is the cow chews the stuff a little bit, sends it down to the microorganisms, and then literally regurgitates it back and makes new surface area available. That's exactly what we're doing. Nature had the solution. We just should have been paying attention. So if you're going to tackle one of nature's hardest problems, you've got to get nature to work for you, not against you. Now, here is a sketch, and I can give you the actual diagram. This upper is the base case payback time in years, as simulated by the National Renewable Energy Laboratory, of the current technology as a function of the scale of production. We're working with NREL on projecting and actually this curve's a little bit too high. It's 2 years, a 2-year payback at 100 million gallons and about a 10-year payback, which is still not unreasonable, at 10 million gallons. And this does not take credit for the many, many, many advantages of being small. You can learn faster, it's easier to raise investment, the feedstock is cheaper, the agricultural environment and ecological integration is easier, so just much, much, much better. There are technical advances, 1 minute. There are technical advances that need to be made in order for this approach to be applied commercially. Most of these are in the realm of biotechnology, and I think that success is quite reasonable to expect with those biotechnological challenges, given on the scale of things, quite a modest investment. I could talk about gotchas. Many anticipated social and environmental benefits have yet to be demonstrated, and negative results are also possible. We have enough rain-fed land, but that does not mean we will choose to use the land that makes sense or in a sensible way. The technology is not yet cost effective, although I think there are things that we can do about that, as I've shown you. What do we need to do? We need on-the-ground projects aimed at realizing social and environmental benefits, which very few commercial biofuel plants were actually motivated by that. We're not going to figure this out with more analyses. We need to learn by doing. Mistakes are reversible, and if we don't have biofuels in our quiver to tackle low carbon fuels, that will not be reversible. We need innovation-targeted R&D, looking at home-run strategies such as the one I've described, but not only that one. Last point, we need to recognize that ethanol is the logical proving ground for new technology aimed at overcoming recalcitrance. It's not the only molecule we might ever want, but the history of the biofuels field is littered with people trying to vault a 100-foot cliff with a 10-foot pole. Ethanol is the place to make this happen, and we've made a huge mistake in turning away from that radically. This is not a religious attachment to that molecule, although I'm fond of it now and then, but why don't I stop there? Thank you very much. I look forward to the discussion.